Let's begin with some thought questions. Here we have a container filled with gas particles, and the current temperature is 420 K, and the current pressure is about 44 atmospheres. I want you to predict what will happen to the pressure inside the container if we were to cool the gas down. Well, if we start to cool the substance down, we notice that as the temperature drops, we see that the pressure is also dropping. They're moving slower, they're going to have less collisions with the sides of the container, and that's going to create less pressure. What if we decrease the volume of the container and left the temperature the same? What should happen to the pressure? Let's notice the pressure is at 45 atm. As we make this volume smaller, but the number of gas particles inside remains the same, we see the pressure increased to 87 atm. And that's because these particles don't have to travel as far to hit the sides of the container. We're going to have more collisions, and that leads to increased pressure. What if we decrease the temperature while decreasing the volume? When we change two variables at the same time, it's much harder to predict what the final outcome will be because decreasing temperature makes the pressure go down, and we saw that decreasing volume makes the pressure go up. So when we're changing two variables of a gas at the same time, we can use the combined gas law formula to see what the total effect of those two changes will be on a third variable. So the formula is P1V1 over T1 equals P2V2 over T2. It's important to remember that in this gas law formula, the temperature must be in Kelvin degrees. We cannot use Celsius. So let's try to use that formula to solve some word problems. And remember, whenever we have word problems, the first thing we always do is make our givens list. So it says the gas volume is 11.0 milliliters. Even if that word wasn't there, we should be able to see the milliliters and know that that's a volume unit. So the first volume, V1, is 11.0 milliliters. And if we keep reading the question, we come to 740 mmHg. So we should identify that as being a pressure unit. So the first pressure is 740 mmHg. And we get to 288 K, and we should identify that as temperature. So that's T1. It says, what is the volume at a new pressure and temperature? So that means our second volume is what we're trying to find, so we're going to make that X. And we see 760 millimeters of mercury. Again, millimeters of mercury was pressure. So our second pressure is 760 mmHg. And then we have another temperature. That's going to be T2. And so we double check. Are our temperatures in Kelvin? Yeah. And then we need to also look at the other units. For example, we have two pressure listed. We have to make sure that those units are the same. We can't put the numbers into the formula for pressure unless both pressures are in the same unit. All right, what was that formula? Do you want to say it with me? P1 V1 over T1 equals P2 V2 over T2. So now we need to take our givens. So P1 is 740. V1 was 11.0. We're going to put that over T1, which is 288. Now, normally we would have the units in these numbers as we put them into the formula, but sometimes when students are first learning how to do this, it makes it seem more complicated than it is. So I'm leaving the units out temporarily, just so we see that we're just doing an algebra problem here. And we're going to have P2, which is 760, times V2, which is unknown, divided by T2, which is 273. So by taking the short time it took to write a givens list with the formula, I know that all my numbers are in the correct place when I substituted them in. In math class, how do you solve this to get rid of these fractions? Cross multiply. All right. So we're going to cross multiply here. So we have 740 times 11.0 times this denominator of 273. That's going to be equal to this denominator, 288, times this numerator, which would be 760 times x. So how do we get 288 and 760 from the right side over to the left side? So we're going to divide 288 and 760, and they're going to cross out on this side. Whatever we do to one side, we have to do to the other side. Now, what I want to do right now is take the units that we had from the givens list and just put them with the numbers where they belong. So 740 was millimeters of mercury. 11.0 was milliliters. 273 is K. 288 had a K, and 760 was millimeters of mercury. So let's look, because if we have a unit in the numerator and the denominator, we can cancel them out. K, millimeters of mercury. The only unit left is milliliters. And if that's what we get as our final unit, we know we set this up right, because if we started with our first volume being milliliters, the second volume has to be in those same units. So now you have two options. You can put these numbers in the calculator in one step and come up with your final answer, or you can multiply the numerators, write them down, multiply the denominator, and then divide. I'm going to do it the second way. So I'm going to multiply 740 by 11 by 273. And that had milliliters with it because that unit is in the numerator. And then I'm going to multiply the 288 and the 760. There is no unit left in the denominator. We've canceled it out. And now to solve for x, I would need to divide these two numbers. All right, so we have a long remainder in our answer. So we got to go back up to the numbers that were in the problem. 11.0 has how many sig figs? 3. How many in 740? That 0 there is just a placeholder because there's no decimal point, so that only has 2 sig figs. 288 doesn't have any zeros in it. Remember, any digit that's not a 0 is always significant, so that's 3. That means 273 without a 0 also has 3. And then we come to the 760 that has a placeholder 0, so that's going to be 2. We got to go with the least number. What was the least number of significant figures? 2. So that's what's going to determine our significant figures. So we need to keep those first two numbers. So x is 10. But does that have 2 sig figs? Now, how do I make that 2 significant figures? I can put a decimal at the end. Now it has 2 sig figs. Or I could write it in scientific notation, and that would also have 2 sig figs. So either one of those would work as our answer. All right, a volume of gas is 50.0 milliliters at 42 degrees Celsius. What is the volume at 130 degrees Celsius? So as we read the question, a volume is 50.0 milliliters. So my first volume is 50.0 milliliters. And then I have 42 degrees Celsius, so that is my first temperature. It says, what is the volume? So that tells me my second volume is what I'm searching for, so that's going to be x. And at 130 degrees Celsius, I should recognize that as a temperature, and that's going to be my second temperature, T2. What unit does temperature have to be in? Kelvin, but these are in Celsius, so I have to convert them to Kelvin before I move any further. And we know that K equals C plus 273. So I'm going to need to add 273 to my Celsius temperatures. So now I need to remember that these are the temperatures I want to use. I'm going to put a box around them so I don't actually accidentally pull that Celsius temperature into my formula. P1 V1 over T1 equals P2 V2 over T2. When I look at the givens list, though, I don't see any pressures. No pressure, no problem. We just ignore it in the formula. That tells us the pressure is not changing. So we can take it right out of our formula. So we really have V1 over T1 equals V2 over T2. So we can easily take our givens, put them in the correct place in the formula. All right, to solve for this, we need to cross multiply, and we're going to have 315K times X equals 50.0 milliliter times 403K. I'm going to divide both sides by 315K. We see that Kelvin, that unit, crosses out. We're going to multiply 50 times 403, and we need to divide that by our denominator of 315. Can we keep all these digits? No, we got to go back up to the problem and figure out how many sig figs can we use. How many sig figs are in 50.0? 3. When it comes to the temperature, I'm not using 42 in the formula. I'm using the Kelvin temperature, which had 3. And I'm not using 130 as the temperature. I'm using the Kelvin temperature, which is 403. So in this case, my answer has to have 3 significant figures. So I'm going to keep the 6, the 3, and the 9. We cut off the 6, but the 6 is greater than 5. So the 9 that I'm keeping has to round up. And our answer should be 64.0 milliliters. There's our answer. So a gas has a pressure of 2.0 atmospheres at 24 degrees Celsius. What is the temperature at 718 millimeters of mercury? So the first thing we do is make our givens list. We're seeing that it has a pressure of 2.0 atmospheres. And even if it didn't say pressure, I should have been able to identify that this is a pressure unit. So the first pressure is 2.0 atm. We see that the temperature is 24 degrees Celsius, so that is T1. What is the temperature? So that means T2. We don't know what it is. We need to solve for that. That's going to be X. And it's at 718 mmHg. Millimeters of mercury is a unit for what? Pressure. So that's going to be P2. We got to check those temperature units. Is it in the correct unit? No, it has to be in Kelvin. Remember, to change to Kelvin, we need to add 273. So that's going to come out to be 297 K. Then we need to check our pressure units. Are they the same unit? No. So I can't use both of those units in the same formula. I'm going to choose to change this to ATM. Well, unit conversions, we use dimensional analysis. So I'm going to set up my problem. I need to get rid of millimeters of mercury, so where is that unit going to go? Numerator or denominator? Denominator. So millimeters of mercury is going to go down here. I'm trying to change it to ATM. So ATM goes in the numerator. All right, so we need to think back to what standard pressure equals. 101.3 kilopascals. It could also equal 760 torr. Could also equal 760 millimeters of mercury. And it could also equal 1 ATM. All 4 of these equal each other. So for the ATM and my conversion factor, I need to pick the 1. And for the millimeters of mercury, I'm going to put down 760. Because remember, in our conversion factor, the numerator and the denominator have to equal each other. I can see they're equal to each other right here. We cross out the units. I can see I need to divide 718 by 760. And that's going to equal 0.945 ATM. P1V1 over T1 equals P2V2 over T2. What variable is not shown in our givens list? No volume. We don't have a V1 or a V2, so we just take them out of the formula that tells us that the volume didn't change. It's not going to be a factor. And then we would plug the rest of the numbers in. So we're going to cross multiply. So now we need to divide both sides by 2.0 ATM. ATM cancels. And we see we need to multiply our numerators, divide by our denominators. The only unit left is the temperature, and we need to round to the correct number of significant figures. How many are in 2.0? 2. We didn't use the 24 degrees Celsius, we used Kelvin, which has 3 sig figs. 718 has 3 sig figs, which means the 2 is what's going to determine our sig figs. We're going to round that to 140. Is that 2 sig figs? Yes, because that 0 is a placeholder. It's not significant because there's no decimal point.